In this video, we're going to take a look at permutation testing, which is just one of the approaches we'll look at in terms of testing hypotheses about population parameters. The main purpose of this one is just to get an idea of what hypothesis testing is, and in particular, what the p-value is and how it should be interpreted. Okay, so here's just an example, and this is two groups of students. Say 6 students show up and are randomly assigned to either attend a specific kind of study session or just to attend a session, let's say a regular study session. After attending the session or not attending the special session, they take an exam. And so here are the scores that were obtained by the 6 students in our sample. For those in group 1, they had 83, 91, and 79. And for those in group 2, they had 68, 74, and 72. And you can see that the scores are higher in group 1 than they are in group 2. But what we want to know is, can we conclude that the population mean, not just the sample mean, but the population for group 1 is greater than the population mean for group B? Like how I switched between 1 and 2 and A and B there. In this bottom section, the first 3 columns, you can see the first column, 83, 91, 79. Those are just the numbers that we obtained in our sample for group 1. The other 19 are the other possible combinations. It's 20 of them. I don't know if you remember from previous coursework, 6 choose 3, that's going to be 20. So we have 20 possible arrangements. The next 19 are the other possible arrangements that you could have for the possible combinations you could have for group 1. Now, this is what you would get, or all the possibilities, if we just took those 6 numbers that were up here and randomly put them into either group 1 or group 2. Here are all the possible combinations you could have for group 1. What we're going to look at now is the likelihood that we would have gotten our result or one more extreme just by chance alone. Well, in this particular example, there are 20 possibilities, and none of them have a sample mean as great or greater than one you have. In fact, well, just one. The one that you have is the only one that has a mean this high. So that means that the chance is 5%. Of course, that's as low as you can get in this, that we would get a mean as high or higher than the one we have for group 1 if we were just assigning things randomly. Again, if we were randomly assigning scores randomly to groups 1 and 2, only one has a combination of 84.33 or greater. That's the combination we observed. Thus, there is a 5% chance we'd get a result this extreme if the test scores were the result of chance alone. Since that's a low probability in this case, what we're going to say is that arrangement might not be due to chance. We think it's not due to chance, and that would mean that the session might be effective at leading to higher scores. Here's another example. Now this time I'm going to state specific hypotheses in a formal sense. HO, the null hypothesis, mu A is equal to mu B. And then HA, the alternative or research hypothesis, is that mu A is greater than mu B. And this time I have 2 groups of size 4. And so the total number of arrangements down here that we have, or combinations, would be 8 choose 4, which I'll just tell you is 70. If you don't know what that means, it's just there's 70 possibilities there. And what I'm doing now is this first one I have the sum. And so the sum of the 4 numbers in the sample that we had for group 1, the actual sample we had, was 317. The next possible sample had a sum of 321. Well, I should have put a yes here next to the 317 because it's as or more extreme than what we observed. But so is 321. By extreme, we mean in the directions, in this case, the direction of our alternative hypothesis. So 321 is greater than 317. So that's as or more extreme. If we pull down here to 310, it would not be. If we got down here to 319, it is. And so what we'll do then is sum up the total number of yeses and divide by 70, since that's the number of combinations. And that will be our p-value, the chance that we would get as high or higher than the one we had by chance alone. The next 2 columns over here do the same thing for mean. And of course, since that's just the sum divided by 4, you're going to have the same yeses and so on as you did before. And then the third set over here is the median. So now I have the median of each of the first of my real sample for group 1 of 81. Of course, I should have yes, because 81 is as or more extreme than 81. And then other possibilities as we go down have different medians. Of course, you can see some that have 81. They're as or more extreme than the median of 81 that we had, and so on. Well, with these specific hypotheses, we're really looking at these columns here, but what I do want to stress here with permutation testing is it's sort of a plug in the statistic technique. No matter what statistic you use, whether it's a sum, a mean, a median, or others, you just get whatever that statistic is for your sample, get all the possible combinations, and then for every sample that you might get, compare that to what you did get, and then the total proportion of, in this case, yeses over the total number of samples, in this case it'll be 70, will give us our p-value, the likelihood that we'll get a result that's extreme if HO is true. That is just by chance. And here's just the bottom of that sequence. We'll have another video that shows this all as a spreadsheet, so if you want to look at the math and the whole data set and everything, you can do that. So of the 70 samples, 9 or 13% had a sum greater than or equal to 17, greater than or equal to 317. That is the sum for group 1 in the actual data. 9 or 13% had a mean greater than or equal to 126.8. Again, that 126.8 was the mean for group 1. And there's a typo here where it says sum in this last one. That should say median. 5 or 7.1% had a median greater than or equal to 81, where 81 was the median for group 1 in the actual sample data. All of those, again, are p-values, likelihood that chance will produce a result as extreme or more extreme than the result that we had. Again, going back here and saying in the direction of our alternative hypothesis. And here's just some graphs to strengthen your understanding here. This is one for the sums. And so these are all, there's 70 dots here. They're all 70 sums that were in the data that we could have gotten from the 70 samples. And you can see that here's 317, and 1, 2, 3, 4, 5, 6, 7, 8, 9 of those were greater than or equal to the 317. So 9 out of 70, this or more extreme. So on this side of that line is the probability associated with the p-value. Same thing for mean, except for now we've got the means marked. And so we had a mean of 126.8, 1, 2, 3, 4, 5, 6, 7, 8, 9 there or above. So this is where we're at. This is more extreme. And we have, again, the likelihood that we would get over there as being the p-value. One of the other things I'll point out about this permutation testing is there's no requirement that we have a bell shape to this. We're just doing an exact calculation of the total number of combinations as the denominator, and the numerator it would just be the total number, in this case 9, of the samples that produce a statistic as or more extreme than the statistic that we observed in our own data. And here you can see with the median, that's certainly not a bell curve, but we can see that of the 70 possibilities, 5 of them had a median of 81 or more. In fact, exactly 81. That was as high as it got in the data set.